Titration of Natural Indicators by Justin+Tavor, D period AP Chemistry. So first off, the question/topic of our lab was, first, what natural indicator should be used for which titrations? And to answer this question, we used first beet solution, blueberry jam, grape juice, turmeric, and geranium petals solution. And the second part of this question is, what are the pKs of these various natural indicators? And the answer to this question is will be shown in the rest of this presentation. So first challenges we had to overcome were first making the indicators. So beets, turmeric, geranium petals, and blueberry jam all come in forms that we can't really titrate it. So first we had to create solutions for these. Second, we had to predict and create the correct concentration of NaOH required so as to prevent the titration from occurring too quickly to get to precise results. An example of this was using, for example, 1 molar NaOH would cause some indicator solutions to instantly change color. And so we had to experiment different concentrations of NaOH. And lastly, titrating the solution precisely to the equivalence point was a challenge because even with the right concentration, one can easily overshoot the equivalence point. And so to get the most precise measurements, we had to titrate slowly and carefully. So some of the materials we used. First, we had 1 molar NaOH. And we also used a burette to titrate the solutions, and a pH probe, and a stir plate, a computer with Logger Pro, a graduated cylinder to create our solutions, or create any solutions we need, of either diluting 1 molar NaOH or creating our indicator solution. We also needed a beaker to hold the indicator as we titrated it. We also needed our 5 solutions of grape juice, turmeric, blueberry jam, geranium, and beet. So here's a picture of our setup. As you can see, we had our beaker, which contained our solution of indicator, and above it is the burette, which we dropped NaOH through into the solution of indicator to titrate it. And inside the beaker is also a stirring rod to stir the solution and make sure everything is evenly spread out inside. And we also used the pH probe, which connected to Lab Pro, which is also then connected to the computer as seen in the second picture. We used this to graph our data. And so our procedures for the setup shown was, first we had to prepare the indicators. And so for beets, we had to shred and boil 1/4 a cup of water of beets in a cup of water. And this is cup as in the measurement of cup, not just any random cup of water. For grape juice, we just measured grape juice out of the can or bottle. And for blueberry jam, we mixed 1 tablespoon of the jam with 1/4 of a cup of water. And for geranium petals, we just cut and boiled the geranium leaves in water. And for turmeric, we mixed 1 teaspoon of turmeric with 1/4 cup of rubbing alcohol. Now, this point is important because, and it's important to be careful at this step and any step in the using turmeric, because this mixture stains. And for example, it stained our pipette, and we had to throw that away. And so the second step of our procedure was diluting the stock of NaOH and HCl to 0.1 and 0.01 molarities. And we created 100 milliliters of each of these to run our 3 trials. And to do this, we used stoichiometry to measure out how small a volume of NaOH we needed and how much water we needed to dilute the water with to create the 100 milliliters of dilute NaOH. And then our third step is, for each of the solutions, we had to do 3 trials of taking 1 milliliter of the indicator, mixing it with the 24 milliliters of DI water. And then, as our fourth step, we titrate the solution mentioned in step 3 with, and after each step, we input a point into Logger Pro to track the change in pH until the colors changed and a full graph was created. And so some of the background info we need for this lab was, first, the definition of pKa, which is the pH at the half equivalence point, or halfway to the equivalence point, and the Henderson-Hasselbalch equation, which is very important. It's the pH equals the pKa plus the log of the base over acid. And from this equation we can derive that when the base concentration equals to acid concentration, log of the base concentration over acid concentration equals the log of 1, which is equal to 0. So therefore, when the pH is equal to the pKa, we know that the base concentration is equal to the acid concentration, which is halfway to the equivalence point. Since also from the definition of a pKa is that the pKa is equal to the negative log of the acid dissociation constant for the solution. So given that, we can also find the indicator's Ka value.
So, as Justin was just talking about the Henderson-Hasselbalch equation, here we can apply that knowledge. With the graphs and knowing the equivalence point of the titration, we can find out the pKa and thus the Ka of any indicator. So with the data we got from our blueberry titration, so this was using 0.01 molar NaOH, we titrated until we reached the equivalence point at 3.6 milliliters. So this, using this, we went back to our data at 1.8 milliliters, and the pH there was approximately 5.1. And since this is the point that's halfway in between the start of the titration and the equivalence point, that means that using the Henderson-Hasselbalch equation, that the pH is equal to the pKa at this point. Thus, we can figure out that the pKa for blueberry indicator is 5.1. And using the equation that negative log of Ka is equal to pKa, we can thus figure out that the Ka for blueberry would be 7.94 E negative 6. The next indicator that we chose to titrate was beet. So this one didn't go quite as planned because the solution of NaOH was too concentrated for this titration. We used 0.01 molar, and thus we were only able to approximate that the equivalence point was at about 0.5 milliliters, and thus we took that the pK would be the pH at 0.25 milliliters, halfway there. And pH at this point would be 7.74, which would make the pKa 7.74 and the Ka 1.820 E negative 8. Our next indicator was turmeric. So this indicator was kind of not overly good of a sample, because what happened was that our solution of turmeric indicator, some of the actual turmeric spice was precipitating out to the bottom, which kind of caused mixing problems and didn't make it a very homogeneous solution. So we're not sure exactly how accurate the data for this one is, but forging ahead, we titrated and found the equivalence point to be at about 1.5 milliliters of 0.001 molar NaOH. Thus the pK would be the pH at 0.75 milliliters, and the pH at this point was 8.98, making the pKa 8.98 and the Ka 1.074 E negative 9. Our third sample indicator was geranium. So this is out of the geranium petals. So titrating it, we found the equivalence point to be at 1.1 milliliters of 0.1 molar NaOH. This left the pKa at the pH at 0.55 milliliters. So the pH at this point was 4.57, and that gave us a Ka of 2.692 E negative 5. So the thing about the geranium one was that there were still very tiny particulates of the geranium petals inside the solution. So again, these little particulates gave it a kind of margin of error. The last indicator that we titrated was the grapes. So this we titrated to its equivalence point, a color change, at with 1.1 milliliters of 0.01 molar NaOH. Thus, we found that the pH halfway to the equivalence point, 0.55 milliliters, was 4.59. Thus, our pKa was 4.59, and our Ka was 10 to the negative 4.59, which is 2.570 E negative 5. So this is just a chart of the summary of our results, and as you can see, all of these are basic indicators. They all they all indicate a color change or an equivalence point that has been reached that's above a pH of 7. So, discussion error analysis. So, one of the main problems that we ran into throughout this lab was that we need to keep on diluting our stock solution of 1 molar NaOH, and since we weren't able to dilute it all at once, these many separate dilutions left us with slightly different molarities of NaOH for each trial, and so none of our NaOH titrant solutions were either very precise nor uniform molarity. The next problem that we kind of faced with this lab was that we accidentally left our NaOH 1 molar stock solution out overnight, uncapped, and thus some of the water evaporated, making it actually a slightly more concentrated than 1 molar stock solution. And yeah, so just an overall note for next time, if we were to do this lab again, then we would use an even more dilute sodium hydroxide solution to titrate, especially the beat indicator, as that one was very approximated. So in conclusion, from this lab we were able to determine that you can figure out the pKa of several natural indicators using sodium hydroxide as a titrant. And additionally, you can use these indicators to in actual titrations to see where the equivalence point is reached. And for example, if there was a titration that you were doing that had an equivalence point of 8.15, you could use blueberry. If the equivalence point was 8.99, you could use beet. 9.39 turmeric, 7.95 geranium, and 7.24 grapes. So yeah, that was our presentation. Thanks for listening.